everybody. What I want you to do today is the final lesson for the exam standard 2.4 or the 91161, and we're going to look at the thermochemistry. So we've looked at substances, solids, and what makes them up, the different types of solids, the particles and the bonding, and then using that to explain the macro properties. You know, are they hard, are they soft, are they high melting points, low melting points. So the final thing now is more on the model side, which is all the calculations. So you need to do really two types of calculations. The one is energy changes using reaction stoichiometry and bond enthalpy, and we did a bit of that last time and we'll do it again this time. So it's bond enthalpy calculations, and then also with differing amounts of substances. So this is where if you've done the 91161, which is calculations in chemistry, comes in, because you do need to know that N is equal to the small m over the big M equation. Because remember, amounts, what is the unit for amount in chemistry? For those of you that have done the CH2000 and 12 booklets. The mole, correct. So now you know where that comes from. Okay, so the first bit here is the exothermic and endothermic, and we did deal with that last time as well, but I just want to sort of revise. If I've got ice melting, now think of where the heat is going. Is the heat going out of the ice to the surroundings, or from the surroundings into the ice? So is this an exothermic, when the heat is going from the reaction outside, or is it endothermic, when the heat is going from the outside into the system? So you can write EX or EN. What would you like to go for? It's endothermic, correct. Okay, because what you're doing is between those water molecules is a type of intermolecular force of attraction holding all those water molecules in position. Does anybody want to have a go at naming the type of intermolecular force, or at least the main type? Just revising what we've done previously. Okay, the hydrogen bond, correct. So these are lots and lots of hydrogen bonds holding the water molecules together in ice. So you need energy to break bonds. So that's why melting is an endothermic reaction, because we need to break all the, not all, but a lot of the bonds holding the water molecules together. So when I say bonds, perhaps forces of attraction is better, so you don't think of covalent bonds. So the forces between the molecules have to get broken, and to do that we need heat to turn water into a liquid. How about that sort of reaction? What type of reaction is that? Is heat going out of the system, or is heat going into the system? So is it EX for exothermic? Okay, it's going out, right, so it's EX for exothermic. Okay, now I know a match is not carbon. It's carbon and hydrogens and oxygens and all sorts of things, but I wasn't going to go for a complicated equation. So if I'm taking carbon, and yes, I'm breaking bonds between the carbon atoms, and yes, I'm breaking bonds between the, well, oxygen gas doesn't have very many intermolecular forces between them, because the particles are quite far apart, and it's only perhaps if they come close together that there might be an attraction. But we've also got bonds, double bonds between carbon and oxygen here. So what's happening is we're forming actually stronger attractions here, so heat is being given out. Okay, here we had to add in heat. So the energy of water as a liquid, does it have more energy than water as a solid or not? Yes. So here the products have got more energy than the reactants. Here the reactants have got less, here the products have got less energy than the reactants because the heat was given out. So this is just quickly going over to work out if it's an exothermic or endothermic reaction is we take the heat that's in the bonds and the products and subtract it from the reactants. And if the products have got more energy, it's a positive number, and that means that actually heat has been absorbed because we've got more energy now in the products. But if it's a negative number, we've got heat being released because the products is now lower in energy. So that diagram hopefully shows might have had lots of energy there, and if I give it out, then it's an exothermic, and if I add in heat, that's now a high energy, so that is endothermic. Any questions on exothermic and endothermic? You understand that in exothermic, the products have got less energy, and in endothermic, the products have got more energy. Yep, okay. Right, so let's go and look at changes in state and see how we use exothermic and endothermic. We've already seen one example of ice melting. So here we've got solid to liquid, ice melting, and trying to explain it in terms of, remember, this is our macro level. We can measure that it's, heat is being absorbed for that. So if we try and explain it on a micro level, what we're saying is we've got to break a lot of these, not all of them, but a lot of these to go from the solid to the liquid. So you'll notice there's still quite a few hydrogen bonds in liquid water. It's just not as many as in a solid. Okay. If I freeze, I go the other way. So I'm going from a liquid to a solid. Okay, so I'm trying to show freezing there. Now, would that be an exothermic or endothermic reaction? So are we making bonds? Remember, whenever we make bonds, it's like two magnets being attracted to each other, okay? So is energy being released, or are we breaking bonds? It's like pulling two magnets apart. So when we make bonds, is energy being given out? Is energy being released, or is it the other way around? Just want to confirm that. So Michael is typing. Yeah, it's being released. So whenever we make bonds, energy is released. So if we're going from liquid water to solid ice, we're making more of these attractive forces. Okay, there's more of them in place. So because we made more, energy has been released. So going from water to ice is an exothermic reaction. If I go from boiling, okay, is this an endo or an exothermic reaction? So to say EN or EX. An endothermic. Okay, so Nicholas, you correct, endothermic. Think of it, to boil water, we have to actually add heat. So we've got to use electricity or a fire or something to try and boil it. Because we have to now, if I now add the gas phase, and can you see we don't have any hydrogen bonds here because the particles are too far apart and they're moving very fast. And that means we've had to break all of these intermolecular forces of attraction to go from the liquid to the gas. So we've had to break more bonds. So we've had to put in energy to do that. So that's endothermic. Condensing is the other way. It's exothermic. I don't know if you've ever sort of had that if you stood in the shower and then you've had lots of steam and then the steam condenses, it's actually quite warm. It's because when the steam condenses, what's happening, it's forming all these attractions again, and that releases heat. Okay, so I'm trying to show condensing there. And then, of course, you've got the sublimation, where you go straight from here to the gas, straight from the gas to the solid. And so, of course, a lot of energy is being released because you're going from no intermolecular forces to lots of them. Okay, so here's now a different sort of example. This came from the last year's exam. Hand warmers contain a supersaturated solution. That just simply means there is just so much solid dissolved in the water that it can barely hold it all. Okay, it's all ready to come crystallizing out. So when activated, so when you press that little button on the hand warmer, I don't know if you've seen those hand warmers with silver buttons on them and you click on them, that's enough to start the crystallization reaction and it gets warm. So if it's getting warm, is it an exothermic or endothermic reaction? Okay, so it's getting warm, so it's giving out heat. So the hand warmer is getting hot, so it's warming your hands nicely. So if the reaction is giving out heat, it'll be exothermic. Okay, does that make sense? Yep, okay, so it's going to be exothermic. Then you have to say why. It just says in exam speak, justify your choice or something like that. But you've got to explain why you said it's exothermic. So, I mean, you could say, well, it releases heat, so it's exothermic. But in terms of bonding, what do you think is happening when something crystallizes? So I've got all my sodium ions and ethanoate ions all separate in solution. And when it crystallizes, what is happening? What sort of bonds am I forming? So Michael is typing there. So just for the rest of you, think of, got all my ions all in solution, pretty close together, and now they crystallize. So my sodium ions, right, ionic bonds are forming. My sodium ions are getting surrounded by ethanoate ions, and my ethanoate ions are being surrounded by sodium ions. So I'm forming a lot of ionic bonds, and ionic bonds, are strong, so there's lots of energy being released, and that makes it quite warm. Okay. This is an example we did last time, where it's basically we're just repeating, breaking bonds requires energy, making bonds releases energy. Hopefully that's in your head now. And you will be getting problems where you've got to either work out whether a reaction's exothermic or endothermic, where you calculate the energy of, say, the reactants and the products or something like that, or they might actually ask you to work out a particular bond energy. And we'll do both examples. So I'm going to be repeating this here. So this is exactly the same question, is calculate the enthalpy change. So this is really, has heat been released or gained overall? Okay, for the reaction between ethene, which is this, and bromine gases, and you are given the average bond enthalpies over here. Okay, they are always positive because they're always taken as breaking the bond. Okay, so they're always given as positive. Okay, so what bonds do we break? The double bond, and there it is, so that's 614. The bromine bond, bromine, and there it is, okay, 193. So we've got 614 and 193. If we add that together, that's going to be the energy involved in breaking those bonds. Okay, making, we did this last time, so I'm just going to go over it very quickly like that. We make 3 bonds, so we break 2 bonds and we make 3 bonds. So it's always good to sort of draw a line down the middle and do bonds broken on this side. Okay, so there's the 614 and 193. So we add it up to 807. It's always good to put units in, and bonds made. And you can try out the calculations at home. Always have a calculator around when you come to these lessons, and just, check, because it's a good way of checking that I haven't made any errors, but also to see that you can use your calculator correctly. Okay, so I've given out more energy than I've used up to break the bonds. So remember, the bonds broken, subtract the bonds made, and so I get, I have done something wrong. Oops, let's go back. What have I done wrong? So see, Nicholas and Michael, it is not negative. Now, I hope you can see, if I subtract 916 from 807, it should be negative. And the negative is also explaining that it is an exothermic reaction. So this would have been marked wrong. It would have dropped me down from an excellence to perhaps a merit because I got everything else right, and it was just obviously a careless error. But always check your answers to make sure you don't do something silly like this. Okay, so here's another one now where I give you the overall enthalpy. In the previous one, you had to calculate it for the reaction. Okay, so here I give it to you, but you have to calculate the average bond enthalpy for the C double bond O bond. So you get given all the bond enthalpies except for the C double bond O. Now, I strongly recommend when you get given something like this that you actually draw out the molecules. Because if you draw them out, you can count much more easily the number of bonds. Because if you look at this, can you tell me very quickly how many CH bonds I have? Just by looking at it. No. I mean, if you could, then you're a genius. But I know I couldn't. I'd have to go, okay, there's 3 there, there's 2 there, there's 2 there. Now, is there anything else? But if you draw them out, it's just much more easy. You can go 1, 2, 3, 4, 5, 6, 7. I've got 7 CH bonds I have to break. I've got 2 CC bonds I have to break. I have 1 CO bond I have to break. And I have 1 OH bond I have to break. And here, I've got 4.5 O double bond O double bonds that I have to break. Okay, how many C double bond O am I forming? It's a bit of a trick question. 6. Well done, Michael. Okay, because I've got 3 carbon dioxide molecules being formed. Okay, and each carbon dioxide molecule has got 2 C double bond O's. So I've got 6 overall. How many OH bonds am I forming? Does anybody else want to have a go? 8. Well done, Chennai. Okay, because I've got 2 OH and I've got 4 water molecules being formed, so it's 8 in total. So it's the same thing, bonds broken. Okay, so I've got 2 CC, 7 CH, 1 CO, and 4.5. Okay, so I suggest writing it out in a very logical manner, so because I find the more shortcut students take, the more likely they're going to make a careless error. So, write it in a number of steps. I know with calculators you tend to want to just all put it in the calculator and then just put your final answer in, but sometimes you forget to add a number because you got sidetracked or you multiplied the wrong thing. Whereas if you wrote it out, then you are going to spot your errors much more quickly. Okay, so bonds made, we do the same thing, but here, of course, we don't know the C double bond O, so you could substitute this as X. You could say, let's C double bond O equal X, and then you can have CX plus 8 OH, and 6X, sorry, 6X plus 8 times that. Okay, so now my equation you have to know is the heat of reactions is bonds broken, subtract bonds made. So you just simply substitute. The heat of reaction comes from up there. Okay, the bonds broken comes from there. And the bonds made is a little bit more complicated because it's in 2 parts. So because I'm subtracting the bonds made, I have to subtract this as well as that. So please don't go minus 6 CO and then plus 3704 because I've got a plus there. So either say minus and then have brackets around here with a plus there, or just go minus, minus. So it's all these little things that can make you go wrong because, it's just, you're not thinking correctly with your maths. So just check those. Now, Jerome, I see you've raised your hand. Is that for any particular thing? Or were you just clicking to see what it did? Because what happens, it pops up to say you've raised your hand. Okay. Right. So now we just solve for the C double bond O. So I'm keeping the 6 still with it. I've taken this minus 6C double bond O, and I've brought it across so it becomes positive, and I've taken this negative number and brought it across so it becomes positive. Does anybody not understand that algebraic step? You know, where I've said I've taken a negative number and brought it over, and the other side it's become positive. You all happy with that? You can say Y for yes or N for no. Okay, right. And then, of course, this stays on this right-hand side, so that sign doesn't change. And now, of course, I've got a 6 over here, so I work that sum out, divided by 6, so I get 4958, divided by 6, and I get 826 kilojoules per mole. Don't forget your units. Okay, and it's a reasonable amount, because if you think of double bonds are higher than single bonds. Okay, you can see this double bond's the highest, so you would expect it to be a higher bond. Okay, then it's always a good idea to write the final step. So bond enthalpy of the C double bond O is equal to 826 kilojoules per mole. I find often students just sort of write a mess of numbers, and you know, they leave out even all this over here. You know, they'll just have equals, 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 and say equals 826 kilojoules per mole. Now, it depends on the examiner, but I know at one stage, if you didn't spell out what that 826 meant, you didn't get excellence. So if you're aiming for excellence, I suggest you always have a final statement to say what that number means. That number means the bond enthalpy, because that's what you have to calculate. Okay. Any questions on using bond energy, either to calculate the delta HR or to calculate a bond energy? Do you think with practice, I mean, obviously we've just looked at 2 examples, but with practice, do you think you'll be able to do it? Okay. So you can always ask for more problems if there aren't enough in the booklet. Now this is the other type of calculation, and this is where you use that N is equal to small m over big M. So it's energy relating to amounts of substance. Because I think you can see if I've just burn 1 peanut, or if I burn 100 peanuts, there's going to be more energy. You know, the fire will be hotter from 100 peanuts than just from 1 peanut. So the more substance I have, the more energy is going to be involved. And we need to know then the moles, the amount. So here's an example from last year's exam. Okay, and it, you know, we don't expect you to know the photosynthesis equation or anything, so they give it to you. Okay, so any equation will be given. Don't think, oh, I have to learn all these funny equations. You just have to know that an equation will be given, and can you work out N and molar mass and so on. And normally molar mass is even given. Okay, as you can see here, the molar mass of carbon dioxide is given. So the first thing over here is, what term best describes this reaction? Exothermic or endothermic? So you will always get a question asking about this. What do you think it'll be? Exothermic or endothermic? Anybody want to have a guess? Endothermic. Well done. Okay, and you know that by a number of ways. It's a positive number, which means that energy had to be put in. If it was a negative number, it means energy would have gone out. So we've had to put in energy because it's a positive number. Others, if you do biology, you'll be able to say, well, it uses the sun's energy, so it's getting energy from elsewhere, so it must be endothermic. So anything along those lines, trying to explain that energy had to be put into the system, would be accepted. Okay, so it's endothermic, and as I said, I've just done the simple chemistry one. That number is positive, so energy is being absorbed. As I say, you could have gone on about the sun, and that was also accepted in the exam. Okay, now this is calculate how much energy is absorbed or released. Okay, now you know it's going to be absorbed because you've said it's endothermic. If 19.8 grams of carbon dioxide gas reacts completely with excess water to form the glucose. Okay, now remember what I said with if you've been for the 91161 lessons, always look for what substance you have to work for. Now they've given you lots of substances there, but the values given or the quantities given in that question only relate to one substance. And what is that? So you get given carbon dioxide, you get given water, you get given glucose, you get given oxygen gas, but actually we can delete a lot of that and we're just looking at carbon dioxide, okay? So we get given 19.8 grams. Now that grams tells you it's a mass, okay? And we get given the molar mass of carbon dioxide of 44.0 grams per mole. So that's a molar mass. So we only have to deal with carbon dioxide and we can ignore the rest. Right, so list everything that's given. It's always good to have a systematic way, and then you really will reduce your careless errors. Okay, so then the next step is, what formula do I use? And as I say, I hope that image will help you remember it's always a small man on top of the big muscle man. Okay, so it's, if I want to calculate N, it's the small m over the big M. Okay, and you should get an answer of 0.450. Now, we haven't finished the question, but try and keep at least 3 significant figures in your calculation, because you don't really want to go down to 2 significant figures and then back up to 3 significant figures. Now, have we answered the question? Can we stop here? No, we can't, because we've got to calculate how much energy is absorbed or released. So we've calculated moles, and as I say, whenever you don't know what to do in a question, calculate your number of moles. That'll get you achieved. Okay, so if you were going, I don't know, just do the list, calculate the number of moles. You may still not know what's going on in that question, but you would have achieved this question. Okay, so I mean, I want you to do more than get more than achieved, but as I say, don't just say, I don't know what's going on here, it's too many words, too many substances, I'm going to leave it blank. Don't do that. Always, as I say, if you get a calculation, work out the number of moles. Right, to work out the energy, we need to look at this equation. Now, we are told that 6 carbon dioxide molecules, or 6 moles of them, because this is always worked in moles, okay? So 6 moles of carbon dioxide give you that much energy, okay? Or not give you, it takes in that much energy. Now, we don't have 6 moles, we have 0.450 moles. So if 6 moles needs that much energy, how much would 1 mole need? Do we divide this by 6 or do we multiply this by 6? Divide. And I think it makes sense. If I've got 6 things giving me this amount, if I've got less, only 1, I'm going to have less being given off. So if 6 moles gives that, 1 mole gives you that divided by 6. Okay? And notice I've dropped the per mole here now. I'm doing it in kilojoules. I know some students go, well, this is kilojoules per mole, but that's 6. Why isn't that 1? A heat of reaction is always written for the reaction. So the unit will always be kilojoule per mole for a heat of reaction. If I halve this, if I said this was 3 plus 3 goes to a half plus 3, then this value would be halved and the unit would still be kilojoule per mole. That's just the convention we use. So I've now moved away from that equation, so I've just kept it as kilojoules of energy. So 0.450 moles is going to give me 1 mole's worth times 0.45. So that gives me an answer of 210 kilojoules per mole. That actually is an incorrect value. Actually, I should have said 210 kilojoules, not per mole, because this, what I'm saying is 0.45 mole is giving me 210 kilojoules. So please, I was not thinking straight. That per mole there is wrong. Are you clear of when to use kilojoules and when to use kilojoules per mole? So kilojoules per mole is when we're working with the heat of reaction for a given reaction, or if we are actually doing the amount of energy for 1 mole. Okay, here we're not doing it for 1 mole, this is for 0.450 mole. Okay, otherwise we just use kilojoules of energy if it's for an arbitrary amount. So let's go to the previous year's question. So here they're combusting, okay. Now you can see we've got two species here. We've got methanol with those two values and that value, okay, because it's when 345 grams of each fuel. So this 345 applies to both types of substances. So it was methanol and there's the ethanol highlighted. So we need to actually think of two different substances. So I like always drawing a line and doing everything for the methanol on one side and everything for the ethanol on the other side. That way you're not going to get muddled between the two. Then, as I say, list everything. It's always a good idea to list. Then think of your N is equal to small m over big M, okay, and do the calculation. So in 345 grams, I have got 10.78 moles of methanol, okay. And now using it, because we want to know how much 345 grams, how much energy will be given off. So we look at this equation. 2 moles gives off that much. So 1 mole would be half of that. So 10.78 is going to be half of that figure times 10.78, and it's 7816 kilojoules of energy. Okay, and there I've used the right unit, kilojoules, because this is the amount of energy given or for a particular amount, not for a particular, just for 1 mole. We do the same thing for ethanol, list the values, okay, you could have even listed the heat value as well, and then we do the same calculation. We now divide by the molar mass of 46, okay, we get 7.5 mole. Now we look at the equation and we've only got 1 here, so 1 mole of ethanol gives you that much. Okay, so I don't have to halve it, I just simply multiply that value by 750 and I get 10.27 kilojoules of energy. And I actually did make a mistake here, so I would not get excellence. And what is that? Does anybody want to have a guess? Okay, I have said it gives or releases this energy, and I put in a negative here, but I actually didn't put a negative in there. Now, you can avoid writing negatives by, if you had said 10,275 kilojoules of energy is released. Because by saying it's released, you're saying it's exothermic, so you're saying the negative. You're just using it in terms of words. Okay? But I didn't do that. I didn't put in the negative, and I didn't do the alternative. I didn't say it's released. So just be aware you should do that in the exam. Okay, so you could say 7.5 mole releases so much of energy, just to spell it out. And of course, remember, for excellence you should give in that final statement, because it says justify which fuel will produce more heat energy. So you say ethanol releases more energy for the same mass. So put in that final statement. Okay, let's do, okay, there's going to be one other slightly different problem, but do you think you can do those sorts of calculations like that's shown over here? Okay, so it's basically, if you don't know what to do, work out moles. Okay, and then you've achieved it. The next step is, for merit and excellence, is to start looking at the number of moles of that substance relating to the heat energy, and then working it out to the amount that you've got, and then you either do a comparison like here, or it's a straightforward one like we did in the previous one. Okay, now you don't have to do the ins and outs of calorimetry. That comes next year. I'm just showing this a picture here because this is the way the chemists find out the bond energies and so on and so forth, and how much heat is being released. So it's either what we call the coffee cup calorimeter, okay, and that's done at constant pressure because it's open to the atmosphere, and it's normally in insulated cups, and you measure the change in temperature. Or it's in a constant volume. This is what we call a bomb calorimeter, and so we say burn something in here. We could say burn the methanol or ethanol in here, and the heat given off is absorbed by the water, and that temperature is raised, and then we can work out the energy involved, and you'll be doing those sorts of calculations next year. What we just do this year is we use this, but it's still to calculate the amount. So here's an example that came from last year's exam. So can you see this is sort of like that coffee cup calorimeter, where you're burning a certain amount of fuel and the water is increasing in temperature. Obviously there's lots of heat loss over here. So do you think this will give an accurate reflection of the energy involved? No. Okay, because it's heat's being absorbed by the metal, it's being absorbed by the air, and it's not necessarily all being absorbed by the water. So that's the question. So we've got a camp stove burning butane gas. He measures the temperature change in the water, and he calculates that when 3.65 grams of butane is combusted, we release 106 kilojoules of energy. Okay, now here's the equation, and the equation is important because of the coefficients in front, and it says calculate the enthalpy change for this reaction based on the above measurements, and we get given that. So how many substances are we dealing with in this question that we have to calculate? Does anybody want to have a guess? Because it's always good when you start off by isolating what are you given. You're just given the butane. All the things are relating to butane, because we've got the mass over there, we've got the heat being released relating to that, and we've got the molar mass down here. So always, and there's nothing else given. We aren't given a mass of any other substance or anything like that. So list that, write your equation, calculate your number of moles. Okay, you've achieved this part. Now you've got to go and do the next step where you've got to say, okay, I've got 0.0629 mole. That releases 106 kilojoules. Okay, I know that my equation has got 2 moles of butane, and I need to work out the delta R. So I've got to change this 0.629 to 2. So basically it's the same sort of thing. If 0.0629 releases 106, then 1 mole releases that much. You divide by it, and I don't want 1 mole, I want 2 moles from this equation. So 2 moles is that doubled, and I get then minus 3368. In the previous one, I wasn't going on really about the significant figures because they really just wanted you to compare whether ethanol gave more heat than methanol. Here they want you to have the delta HR. So one way of getting that to 3 significant figures is to say 3.37 times 10 to the 3, because that clearly shows the 3 significant figures. You could have rounded that off to 3370 to get 3 significant figures. But then you can start arguing, was it exactly 70 or was it, around there? So using scientific notation spells out very clearly what your how many significant figures you've got. Okay, and I think that actually is the end of our slideshow. So we finished a bit early today. And I'm just going to go straight back to, sorry, my very first slide over here. So we've done the enthalpy changes with the differing amounts of substances. We've looked at changes of state, so you need to be able to say, is freezing exothermic or endothermic, and why? Okay, and then doing the making and breaking of chemical bonds, which could be via bond enthalpy, or it could be what we did just now, like that butane and so on. Are there any questions on that? Do you feel confident you'd be able to do these sorts of calculations? Okay. Is anybody stuck on these calculations because you haven't done the 91161? I mean, you haven't done the CH2011 and the 2012. You all otherwise you are all okay. Okay. No response. Okay, so we'll stop there. Next week for the Tuesday slot, I'm going to go on to the next exam. And would you like me to do the organic or the other one? I did have in my survey more people wanting the organic, but it could have changed now because that survey was done some time back. Okay, people would like the organic, right? So we'll keep the Tuesday slot for the exam, and then, as I say,